So with all of that implementation detail, now we're ready to see the same English sentences, but written in terms of records. So here we go. The recursive resolver asks the same question as they always ask. What's the IP address of eeks.berkeley.edu? And the root name server sends the same 3 sentences. So here they are in English for you one more time. The first one is, I don't know, talk to the .edu name server. Here's their name. Here's their address. The second one is, I want to delegate trust to the next name server, so I'm going to sign their public key. So if you trust me, now you trust them because I've signed their public key. So anything that is signed using that public key is now trustworthy as well. And finally, here's my public key for signature verification. Those are the 3 things in English. On the bullet points, you can see what they are in records. How do you say, I don't know, talk to this next person? You use an NS record and an A record. Same as regular DNS, no change. How do you send a signature on the next name server's public key? We just said that sending a signature requires 2 records, sending a certificate rather. So the certificate comes in this pair of records. The first one is type DS. It includes the next name server's public key. There's a weird hash, we don't care. It's the next name server's public key. And then the RRSIG record signs the DS record. These 2 things together are the code equivalent of, here's the next name server's public key signed by me. If you trust me, now you trust them. Here it's written in records. And finally, the root name server has to provide its own public key, so it uses that handy DNS key type record to encode its own public key. There it is in records. So it's just English changed to records. OK, now we talk to the .edu name server. We ask the same old question, and we get an answer that looks pretty similar. Once again, in regular DNS, as in DNSSEC, we say, I don't know, here's the next name server. They are for berkeley.edu. Here's their name, here's their address. That uses an NS record and an A record, like it always does. Then you send a signature on the next name server's public key. And this is a certificate that says, if you trust me, now you trust them. This is done using 2 records, like we talked about. First, the DS record tells you what the next name server's public key is, with a hash that we don't care about. And then the RRSIG record signs the above DS record. And by signing the above record, you've signed their public key, or a hash of it. And that's how you get trust on the next name server. And finally, the .edu name server provides its own public key for signature verification purposes. Here was a signature. Here's my public key so that you can verify the signature that I sent above. One little footnote, because sometimes people ask, and if you don't want to listen to this, just don't. But the reason why the .edu name server has to send its own public key is because back here, when the root name server sent this DS record, the public key was hashed, and you can't reverse the hash. So the .edu name server, and really every name server, has to send their own public key. Kind of a footnote, but that's why we designed it this way. OK. Final step. We go to the berkeley.edu name server, ask them the same old question. This time, we get an answer. The answer is encoded in an A-type record. Here's their name. Here's their IP address. Great. That's our answer. And once we have the answer, we should sign it. So the berkeley.edu name server signs the record. And as always, the berkeley.edu name server provides its own public key for verification purposes. The signature uses RRSIG type, and the public key uses DNS key type. So that's the whole story going top down. Now, since we're here doing this lookup, one other cool thing you can do is actually run the lookup kind of in reverse. And we can show you how the recursive resolver gains trust on this record. So we'll do the same steps, but in reverse. And we'll show you what a recursive resolver might do in order to verify that the answer they received is correct. So let's say all the steps are done. The recursive resolver went back and forth and collected all of these records. The recursive resolver must have a dozen records at this point. They've collected so many. How do they know that this A record is correct? So they see this A record, and they're not sure if it's correct. It just has an IP address and a domain name. There's no cryptography on it. What if this is wrong? How does the recursive resolver use all of those records it's collected to know that this answer is correct? So here's what it might do. First, it sees this A record and says, I don't know if this is correct, but I have a signature on it. So I could just use this signature to check if this record is correct. Great. So I'm going to use this signature and verify on it to see if it matches the record. What public key do you use to verify this signature? Well, who signed this A record? It was signed by the berkeley.edu name server, so I should use the berkeley.edu name server's public key to verify the signature. Well, luckily, that's right here. I received that record too. So the recursive resolver's first step, if it wanted to verify all the way up, would be to use this public key from berkeley.edu to verify this signature to check if this record is correct. If it's correct, we're in business. If this is wrong, then we know someone has done some tampering. That's the first step. Can we stop here? Well, how do we know that this public key was correct? What if this was a bogus public key, like an attacker's public key? So how do I know if this public key is correct and not an attacker's public key? Well, luckily, somebody told me it was correct. Who? The .edu name server. The .edu name server said, here is a hash of their public key, and I signed it. So therefore, if you trust me, now you trust them. So because I have this certificate, I can verify this certificate to check that this DNS key record is actually correct and not a fake berkeley.edu public key. So I want to be able to verify this. By verifying this, it will give me trust on the public key that I used earlier. How do I verify this signature? Well, who generated this signature? Who signed it? The .edu name server signed it. So I should use .edu's public key to verify. How do I know .edu's public key? Oh, they provided it to me right here. So I'll use this public key to verify this signature. That gives me trust on this record here. That's how I know that the berkeley.edu public key was correct. But wait a minute. How do I know that this public key is correct? What if this isn't the real .edu and it's some attacker? So I should verify this public key as well. How do I know that this is the correct public key? Well, luckily, someone earlier told me that it was the correct one. That was the root name server. They sent me a hash of that same public key, and they signed it. So if I verify this signature, it should help me confirm that it's the correct public key. So I want to verify this. Who signed this? Well, the root did. How do I know the root's public key? Either use this DNS key record, or it's hard-coded. Either way, I use this public key to verify this signature. Now I know that the .edu public key is correct. But wait a minute. How do I know that this public key is correct? OK, well, we can stop here because this is the root of trust. Remember that everyone automatically assumes that this is a trustworthy public key. It's a piece of information that everyone knows. We have it hard-coded. So if something is signed by this public key, you just automatically trust that it's good. So because we've checked all the way back up, and our A-type record had signatures that were signed by other signatures that were signed by other signatures, all the way back up to this original trustworthy root public key, we know that the answer is correct, and we've successfully verified the integrity of our record. We stopped all of the malicious network attackers and all of the malicious name servers. So that's how you would verify the record. You could do it bottom up if you wanted to. Now, one final little question sometimes people ask is why we don't sign these records, the NS and A-type records. You could if you wanted to, but if you look at the steps that we took, we didn't really need those signatures to verify this final answer. So DNSSEC doesn't sign those records, although I guess you could if you wanted to. But that's the whole story for how DNSSEC works with all of the record types. So it's a neat little exercise in seeing how you can extend an existing protocol to add some useful cryptography on top. I think it's a pretty clean design, all things considered.